you want to take one?
Buenos días a todos. Vamos a empezar con la presentación de Konstantin y Hicke en el thesis. Konstantin.
Thank you everyone for coming to this defense, and I would like to especially thank this committee for being here to evaluate my work. So, like the thesis, the title suggests, this thesis is about semiconductor lasers. Everyone knows semiconductor lasers because they're all around us in our everyday life. Many things that we do involve in semiconductor lasers, whether we print our papers, we go dancing in disco, lasers. Okay, this is maybe not semiconductor laser, but who knows. But from our perspective, the semiconductor lasers are interesting or fascinating devices from a dynamic perspective. The dynamics come from delayed optical feedback or delayed optical coupling, and this delayed feedback or coupling can lead to a multitude of different dynamical behaviors like periodicity, pseudo-periodicity, and even chaos. And in that way, semiconductor lasers are also very well controllable and interesting testbed systems to study. In that way, they're very well controllable, and we can use them to address fundamental questions of delay systems or of complex systems. One question would be about synchronization. How can we synchronize complex dynamical systems, or the dynamics of those, or even chaos? What do we have to do, and how does synchronization degrade? And we can also pose questions or answer questions about determinism and under the influence of noise in the system. And also, due to the interesting dynamical aspects of semiconductor lasers, delayed feedback systems or delay systems with semiconductor lasers allow for interesting applications to later. This work involves experimental work, numerical work, and even some analytics. Let me show you the outline of my presentation. First, I will introduce the single semiconductor laser with delayed feedback, show some characteristics, modeling, and dynamics. Part 2 deals with synchronization of two delay coupled systems, the influence of asymmetries, synchronization stabilities, and synchronization dynamics. Part 2 now where we use synchronization of delay coupled semiconductor lasers deploys semiconductor delay system, the dynamics of those delay systems for photonic data processing using transient dynamics. Let me start with a solitary semiconductor laser. So this is a laser without any feedback, so just standalone, and some characteristics of those is, for example, a narrow spectral line width of the order of tens or hundreds of kilohertz. We can see here this is an experimental optical spectrum. Semiconductor lasers have a linear pump power characteristic, so if we increase the pump current from the laser threshold on, there is a almost linear relation between oscillations. These are oscillations between the optical field and the carrier inversion in the laser. So if we have, by some perturbation, by a pump pulse or by noise, a deviation from the stable emission, the laser returns via these damped relaxation oscillations to the stable output state. And also, the laser exhibits an intrinsic nonlinearity, which is usually expressed via the alpha factor, and this manifests itself in the amplitude phase coupling. So alpha would be the nonlinearity of the laser. So what happens now if we get delayed optical feedback from it is being fed back into the laser? Certain things occur. For example, the additional the light reduces the power, the pump threshold, so the lasing threshold. We can see that here, the red curve. The feedback broadens the laser spectrum to a great deal. We can see that here. So this is the solitary, and this is the spectrum of a laser with feedback. This can be up to 5 orders of magnitude, the line width. And most interesting is that delayed feedback can or does incite instabilities in the laser. So it leads to complex dynamics, which is called the Lang-Kobayashi model. And these are rate equations for the complex electric field amplitude E here, and the carrier number N. And these are coupled delay differential equations, which have certain assumptions which make it simple. For example, it's only for single mode output, single mode operations. It works, or it is applicable for low to moderate feedback because multiple reflections are not accounted for. And also it's a kind of a mean field approach because spatial effects, for example, are not accounted for. So feedback terms, so here's the electric field amplitude of the time t minus tau, so the delay time, with the coupling strength here, feedback strength. And this is a noise term. This is a standard Langevin noise term, so it is modeled as Gaussian white noise at zero mean. And yeah. Here in the carrier equation, we have here the pump current, which is kind of important. Here's the carrier decay, and here again the gain. And the interesting, or the remarkable assumptions that are made. Let us move on to the basic solutions of that system. These are called external cavity modes, ECMs, and these are characterized by this ansatz here. This is in a d-dimensionalized form, but it works the same. So we have a constant amplitude A, we have constant frequency omega, and a constant carrier inversion N. And if you solve that, then you have this kind of solution. So you have a transcendental equation for the frequency, and here's the equation for the carriers. And we see already here by this sine term, and here the combination with the cosine term, that the shape of these solutions will be an ellipse in the frequency carrier phase space. So here we have the frequency, here the carriers. These solutions are periodic orbit, and the parameters that we have here in these solutions, the laser and system parameters, they affect the position of these ECMs in the phase space and also address the dynamics. So with changing these parameters, you can change the dynamics. These green modes here are called modes. They come from this constructive interference in the external cavity, and these are anti-modes. These come from destructive interference. Okay, so a good thing about the simple model was that actually it explained the origin of, or it occurs for a low applied pump current close to the threshold at a moderate feedback level. What we see here is an experimental time trace. So we have here in blue the fast fluctuations, and here sudden dropout in power. You can see with this red line here, which is a low pass filtered signal, which then more shows the power characteristic, that there first is a build-up process, then you have this plateau here, and then sudden rapid power dropouts, and these occur irregular, how these power dropouts come to be. So here we have a numeric time trace of one of these LFF structures, and here the power dropout, and in the lower panel we have the frequency evolution. The time is here measured in photon lifetimes in the numerics, and we see that the build-up and the dynamics here are correlated with the drift towards lower frequencies, and at the power dropout the frequency jumps. If we put this now in the phase space, like that, and then we have a sudden power dropout when the trajectory comes too close to an unstable saddle node, so to an anti-mode, which are actually saddle nodes. And we see here two different dropouts, just to emphasize that these are irregular and in no way occur in the same place in phase space. After this process, everything starts over again, and this repetition or repeating pattern is the reason why it was called Sisyphus effect. And you can see that the dynamics are quite different. So they're much faster and more irregular even, and they don't have this repeating pattern of the power of the power dropouts. The corresponding frequency dynamics here are also less regular, and we can see that here in the phase space that the dynamics are more restricted to a narrower region of phase space, and these jumps here, or these excursions, basically happen with the same mechanism as with the LFFs. So the dynamics come to. Okay, so let's sum up the introduction. So we have seen that semiconductor lasers with delayed feedback can exhibit complex dynamics, rich complex dynamical behavior, including chaos. That the dynamics are influenced not only by the deterministic mechanisms, so the feedback, but also by the intrinsic noise. And dynamics can be addressed by key parameters of the system, like the feedback delay, the feedback strength, and the pump current, which are all accessible also experimentally. And I've shown you the characteristics of the LFF and K-chorus collapse dynamical regimes. Okay, so pose some fundamental questions about delay systems, for which we can now use semiconductor lasers as test systems. For example, can delay dynamical systems be synchronized? If yes, how? How can we do that? And what are deteriorating effects? So how is synchronization lost, or how does it behave over time? For which we will check also on the influence of asymmetries in the coupling setup, for example. So how do we synchronize the dynamics of two delay coupled semiconductor lasers? One would think we just couple the output of one laser into the other laser and vice versa, right? So we have a coupling delay of tau, but is induced by the delayed coupling, but there's no identical synchronization. So the lasers do not behave identically. We can achieve that by a so-called relay configuration. So if we put in the middle of the, in between the two lasers, a relay, for example, a semi-transparent mirror or a fiber loop, then well, it's easy to see that the lasers basically, they both feed the reservoir, and then both lasers get the same output from the reservoir. For example, in a semi-transparent mirror, parts of the light is reflected, comes back to the laser as feedback, like synchronization, or that can occur. So if it's exactly in the middle, then the lasers receive exactly the same input at the same time. And it's easy to see that this setup corresponds to that one. This is just a reformulation, basically. So we now analyze the stability of synchronization in this scheme by using a generic approach. So here we have equations for two states, state vectors x1 and x2, which would take the place of the lasers. So in this case, they would include the field and the carriers. Here we have a function with a feedback strength L and here the delay, and this is the coupling term with feedback with coupling strength K, also the delay tau. C is a coupling matrix. In this case, applies that such that the fields are coupled, not the carriers. So we define now new variables S and A, one being the mean basically, and one is the difference, and then the evolution of these variables describe the dynamics in the synchronization manifolds, the synchronized dynamics, that would be S, and A would that you see this term here, L minus K. So there's a point that if the feedback and the coupling strength are mismatched, that there will be some deteriorating effect on the synchronization. And indeed, this is a very possible symmetry also in experimental systems. For example, consider the semi-transparent mirror. If the transmission and the reflectivity are not equal, then we would have this kind of mismatch. And like I mentioned, this term would then lead to the deterioration of synchronization, because we have this delayed feedback term that could reinforce versus the feedback strength and the coupling strength. And we see here, this would be on the diagonal, we have the non-mismatch case, and we see that there's degradation or deterioration of the correlation, so loss of synchronization quality if you move away from the diagonal. We can also see from these equations that in the synchronization manifold, so if both lasers are synchronized, then A would be 0 here, right? that the coupled laser system would then behave like a single delayed feedback system. So one laser with feedback strength L plus K. So let's now assume we have the sum L plus K is constant. And this is now projection onto the synchronization manifold. The blue lines here is the dynamics that are synchronized, and the gray part is the unsynchronized part. And we see that actually corresponding to the power dropout before, we see synchronization occurring at the power dropout point. These modes here now, the color coding is, the green ones are the transversely stable modes, and the red ones are transversely unstable anti-modes. And we test, or we calculate this transverse stability via a variational equation with the transverse perturbation delta. And here again we have the mismatch of L minus K, if there is one. In this case there is one, so we have here a mismatch between feedback and coupling, and we see that several modes have been destabilized by this mismatch, and we see that when the trajectory is in that region, then the dynamics between both layers is desynchronized or unsynchronized. But we can also see that another possible asymmetry that also applies very often in experimental systems is a feedback delay mismatch. So what would happen if you basically move the relay away from the center between the two lasers? Then both lasers would have different feedback delays, right? Tor1 and Tor2. If we now look at the stability of the synchronization of that system, we reformulate these equations concurrently. Here we have a longer delay and a feedback delay, and here a shorter one. And we can already see that there will be corresponding to this delay mismatch. Then it can be shown that we have identical time-shift synchronization only if the feedback and the coupling strength match. Then the transverse stability can be calculated like this. So there's no dependence on a delay term, only the dynamics are in here. But does that mean that the delay mismatch does not have the effect on the synchronization properties? This is a numerical time series with an applied delay mismatch. We see the excellent or the perfect synchronization because this was simulated without noise. And also if we now, for an exemplary case where the delay is 1000, we calculate or we compute this the value of this peak in the cross correlation function at the respective delta Tor over a whole range, so from no mismatch to the maximum mismatch. This is the red line here. We see that there's almost no change, so unaffected. So we can say that the delay mismatch does not affect much the synchronization quality. But there is some change here, and especially we have these peak structures. So for very small mismatch, for one delay being very short, the other one very long, and at some certain ratios between the feedback delays. And indeed, if we now plot the dynamics in phase space, we can see that there's a stabilization or regularization effect, which is based on destructive interference. If we apply, for example, here a small mismatch, the dynamics get stabilized to a single mode at a rational ratio, here as well, and also for a very large mismatch, so one delay time being, feedback delay being almost zero. First we had the ellipse, right? But then if we change the mismatch, the change alters, and this then alters the dynamics. If we now apply a combined mismatch of the coupling and the feedback and the delay mismatch, then we see here, by the same kind of plot we had earlier, that the synchronization now is much more sensitive to the coupling asymmetry. So we still have regions of very nice correlation, very nice synchronization, but the region is much smaller than, for example, one should really adjust the coupling and feedback strengths accordingly. So, but if now the coupling is symmetric, the lasers are identical, and the synchronization manifold is stable, transversely stable, do we then always have synchronization? The answer is no, because there's an effect called bubbling, attractor bubbling, which is noise induced, can also be induced by mismatches in parameters. And this bubbling induces intermittent desynchronization events. So even if we have completely identical systems that are completely symmetrically coupled, since there's noise in both systems, we still have intermittent desynchronization events. And I will now show results from experiments here one laser and one laser being coupled to this loop, and the other one as well. The symmetry was maximized to as much as we could, and this loop here now takes the place of the relay. So both inputs of both lasers are coupled into this 50-50 coupler, going into this loop, and then both signals are distributed evenly into both lasers. So this accounts for symmetric feedback and coupling. And this is one experimental intensity time series. So the black and the red line, and we see excellent synchronization. I cannot emphasize this enough. I mean, if you look at this, there's almost no difference to be seen, and there's a considerable synchronization error. This would be a bubbling event. And we want now to test, or we want now to evaluate the synchronization or desynchronization characteristics with varying pump current. So we start with low pump current, so the low frequency fluctuations regime. These are experimental time traces as well. So we have the fluctuations here, and the power dropouts. And the lower panel show the momentary correlation. This is called the sliding window cross correlation, and this through the entire time series. And then we see these dips here, right, where the lasers desynchronize. So this type would be a zoom, and the desynchronization takes place at the power dropout of one laser, and the lasers then desynchronize for a duration of the order of tau. For statistics later, we will consider a drop of the sliding window cross correlation below 0.5 as instituting a bubbling event, and for a long time. Now for an increased pump current, we have again the Courant's collapse regime, and accordingly it's much faster dynamics. We also have faster desynchronization, so more frequently occurring desynchronization correlation peaks dips here. This again is so due to the increased frequency. Now this illustrates again via statistical measures. This is the bubbling interval, so the spacing between the desynchronization events, and with increasing pump current here. P is the normalized pump current, so 1 would be threshold, and so on. And we see that with increasing pump current, the bubbling events become more closely spaced. So they occur more frequently. Concurrently, the fraction of the sliding window cross correlation above this threshold 0.5 decreases. So let's sum up. We have seen that one can synchronize two delay coupled semiconductor lasers with zero lag in a symmetric relay configuration, and that the more symmetric the setup is, the better it is, or the more identical zero lag synchronization is favored. We have seen that different asymmetries have different effects on the synchronization stability or the synchronized dynamics. And we have also seen that the system exhibits a phenomenon which is called bubbling that leads to intermittent desynchronization even in the case of symmetry. Okay. Now that we have found so many characteristics, or namely, what we have is dynamics time series with significant events that occur erratically. In this case, the example would be the LFF power dropouts, and we know that there's also noise in the system. So what we want to know is what can we say about these power dropouts? Which ones are mostly induced or driven by noise, or which one are induced by deterministic chaos, and which ones are not? About these power dropouts, because there was always controversy because the bubbling dropout statistics, they show stochastic properties, but also with the modeling approach, one can show that the dropouts are reproduced by a purely deterministic model. So if you do not have noise in the system, you still have the dropouts. Other groups and other people have applied methods to test for statistical measures. For example, the group in Barcelona has applied ordinal pattern analysis to test for this. What we do here is an event-based approach, so we check every single individual power dropout event and assign whether it is deterministically driven or not. And the method works like that. So first we identically synchronize two semiconductor lasers with zero lag. Then we know that the dynamics correspond to a single semiconductor layer with feedback, just with the corresponding double feedback strength. But also we have noise, which is independent for each laser in both systems. So both are influenced by their own noise. Here we have synchronized power dropouts. This is again the desynchronization of order Tor, but it can also be shorter. Then we say if the power dropouts is synchronous, the dropouts are deterministically driven because if they were noise driven, this is basically impossible or very, very, very unlikely because the noise is independent. And yeah, if they're not, then there are several possibilities which I will go into later. This was then more or less it works the same as the one I showed before. And in this experiment, I was very careful to adjust the delay times and the coupling strengths as much as possible. Actually, the delay length was down to a precision of ½ centimeter, if I remember correctly. And these are now our experimental results. What we see here is the fraction of the synchronized power dropouts, so the fraction of all the measured dropouts versus the normalized pump current, so versus relative to the lasing threshold. And what we see here is that closest to the threshold, the fraction is highest with the values were synchronized. So 85% we assign as being deterministically driven. And we see also a decrease here with the pump current. But what does it mean for all the others? So especially for this region here where we have lower fractions and even the ones that are not accounted for here, what does that mean? Does that mean that they are driven by noise? That is not necessarily true because as we know there is bubbling in the system and bubbling leads to a dynamics transverse to the synchronization manifold. So in this way the dynamics cannot be identified with the single delay system dynamics anymore, so our method loses applicability. There might still be some small magnitudes could affect these results, and also sometimes the experimental uncertainty. So sometimes where the power dropout occurs is not completely clear, and since we are working on a 1-2 nanosecond precision, sometimes uncertainties can be greater. Always, when in doubt, when in doubt whether the dropouts were really synchronized or not, it was always assigned to being non-synchronous. Because of these reasons, then, we can say that the obtained fractions here are only lower limits of the synchronized dropout fractions. We can assume that the actual fractions are higher, right? We will test this with numerics, with simulations. What we have here now is the same kind of Lang-Kobayashi equations we have seen before, just now a system of two coupled lasers. So two field equations, two carrier equations that have their own feedback terms here, feedback strength. Here are the coupling terms, so laser 1 to laser 2 and vice versa, and each have their own noise source. Again, being modeled as a large laboratory. Here we show the numerical results. These are the synchronized dropout fractions, again changed or varied noise strength, which is in this case called spontaneous emission strength, as the y-axis. What we can see is that the maximum of this fraction, the same as in the experiments, is still close to the lasing threshold at 1.0. But we can also see that these values are all very large, right? By the color coding, we have very large fractions, which are much higher than in the experiments. We can also see that the results are pretty robust against noise. So noise up until a certain value does not have much influence. And for the type of laser we use, noise strengths in this region here are thought to be realistic, 10 to the minus 6, 10 to the minus 5. Include mismatches in our simulations, so of the order of 1% in the delay time, in the coupling strength, in the alpha factor, and in the pump current. So some system parameters, but also one laser intrinsic parameter. We see that the fraction values decrease massively. We still have the maximum close to the lasing threshold, but we have much smaller values for larger pump currents. But we can also see that it's still robust up to the realistically thought noise. Now here the gray one without any mismatch, red with mismatches, and the blue ones are the experimental ones. We see a much nicer correspondence here. And So that would indicate that in the experiments there actually might still or probably have been asymmetries and mismatches left. But this reinforces only our statement that the obtained fractions are lower limits. So if in theory it was possible to completely symmetrize in experiments the setup and the laser, we have used serial synchronization as a method to identify individual deterministically induced power dropouts, or basically assign determinism to single individual power dropouts. We have seen that the fraction of these deterministically driven power dropouts are highest close to the threshold, and with a value of up to 85%, not up to, minimum of 85% deterministically driven. So here that's an error. And because of the limitations I listed, these obtained fractions can be considered the lower limits. So in reality, or hypothetically at least in reality, we have with photonic data processing using transient semiconductor laser dynamics. I know that's a mouthful, but I will explain and be careful to be precise. So what we do here in this part of the work is that we evaluate the computational capabilities of a single delay system, a single semiconductor laser to be exact, with feedback within the scheme called reservoir computing. Reservoir computing is a comparable novel concept for computationally hard tasks, for example, pattern recognition, like face recognition, speech recognition, handwriting, and so on. And this the different parts of the brain and how they interact. And it's utilizing nonlinear transient dynamics, so the transient behavior of the dynamics of complex recurrent networks. What does that mean? Okay. So the concept is based on the projection of a low-dimensional input, like a speech pattern, onto a high-dimensional state space. This is traditionally done with a large networks of coupled nonlinear nodes. This is called the reservoir. And this reservoir is being injected with information, which is really random. And so is are the connections between the nonlinear nodes in the reservoir. What is not random is the readout layer. This is basically where the information is extracted from the system, from this core reservoir part. And these readouts are weighted. So each state of each individual nonlinear node is read out, and the weights of each readout is trained. Training, what does that mean? I mean, they don't go to gym, right? And the readout weights are then optimized to a certain target, or to the target that we know, via linear regression. And after these readout weights are trained, we can then test the performance of the reservoir. So we use previously unseen data of the same kind. So if we formerly used speech patterns, we again use speech patterns of the same kind. The readout weights are trained. The other connections stay fixed. So this is basically one fixed standing system, and only these are altered. And the readouts can be trained or have to be trained for each for each computational task that is applied to the system. In that way, for different tasks, that is for different samples, different features of certain input samples can be classified at the same time just by using different readout weights. And since this is done in post-processing, so with the computer until now, we can do parallel processing. There are several necessary properties of reservoirs for reservoir computing. One is the approximation property. That basically just means that we have to have similar response of the reservoir, transient response of the reservoir to similar inputs. We have the separation property. You can tell them apart. And also fading memory is necessary, which is basically short-term memory, which can be, for example, applied by delayed feedback, so that all the data can be processed in the context of the past inputs. So, a large reservoir to do this experimentally is hard to do, right? Because so many nodes, how do we do this? And within the framework, we use a single node delay system. So, mathematically, delay systems are infinite dimensional, In reality, of course, they're not, but very high dimensional. And what is done is that we basically emulate a network in the system. So we have here the delay line of length tau, and we define n positions in this delay line called virtual nodes, which are separated by a time theta. And these will then now, these virtual nodes will take the place of the nonlinear nodes of the, as we do not spread information to different nodes in space, but in time. And the choice of the theta is very important because it determines how the neighboring nodes in the system are coupled. This single delay node system for reservoir computing has been implemented successfully already in many experimental systems. There have been realizations with electronic circuits using MRK glass nonlinearity. There have been experiments with optoelectronics in our lab, and also by another group with semiconductor optical amplifiers. And all these experiments, they resulted in very attractive results for this concept. And this was why this was why we would like to improve this very basic setup with a single delay system with feedback. And look what we can do. We check the performance in two benchmark tests. One is isolated spoken digit recognition. So we have speech samples of the numbers 0 to 9 uttered by 5 different female speechly able to classify it as the right number. The other task is time series prediction. So we have from an experiment a kind of erratically occurring complex dynamics. And the task for the reservoir is to do a one-step prediction of this time series. And these two tasks are very common in this community, and they are considered computationally hard for traditional systems. These are the results that were obtained here by Daniel Brunner in the lab for the spoken digit recognition and the time series prediction. For the spoken digit recognition, we have as an indicator the word error rate, that the minimum of the error, so the best performance, is again close to the solitary threshold, so that without input we are actually more or less in a stable state, and it increases with pump current a bit. And for the case of time series prediction, which is measured by the normalized mean square error, we also have a similar characteristics. So first we have the minimum here close to the threshold, and then a sudden rapid increase with the pump current. With simulations now, we can find even better suited conditions for experiments. Maybe we can access parameters that are not accessible by experiments, as intrinsic parameters, for example, and we can gather. But this time we use a two-mode model. So we use two different modes, parallel and perpendicular, for two different polarization directions, that we can account for not only what we formerly use as standard optical feedback, which we call polarization maintaining optical feedback, PMOF, but we can also account for polarization rotated feedback. So we rotate the polarization in the feedback path, and then the feedback goes from the dominant mode, the parallel mode, into the perpendicular mode. We have also tested two different kinds of data injection methods. The optic modulator, for example, Marzenda. And these are now our results from the numerics, or some of them anyway. For the spoken digit recognition, we have here the electrical injection case, and we see that that close to the threshold again, we have the best performance, the minimum error. But we can also see that the case without any feedback actually performs best. So by this, we can see that the speech recognition task actually does not seem to recover word error rate, and then it increase here. And this qualitatively corresponds to what we saw in the experiments. Now for the time series prediction, we again check versus the normalized pump current for two different feedback forms, so PMOF, polarization maintaining, and polarization rotated. We see that close to threshold, for PMOF at least, we have the best performance, and then a very big increase in error, and PROF actually performs a bit better. We can now improve this by doing what before we used for classification, the complete power output, and use them both for classification. And then we have additional information. So if we compare the light-colored symbols are the results for a total output intensity readout, and the darker ones are for now the separated ones. And we see that for prof, the performance actually increases massively. So we have a huge increase in performance if we use the separate readout. On the other hand, if we use the polarization maintaining, the second mode does not get stimulated much, behaves noise-like, and then we have just a bunch of redundant information that is still used for the classification for the readout processing, and that actually hurts our performance. Another way of optimizing the performance of the system is the node separation, theta. I mentioned that it is important. The one with the ellipse is the value we used for most of our numerics. That would be 200 picoseconds. But we see that with this dependence of the normalized mean square error for this for the time series prediction, we see that there's actually a better suited value here. So a much shorter separation of the nodes, we can obtain a much lower error value. And kind of concept. And if theta is too small, then the nonlinear node does basically not have time to react to the input. So the response of each node is very small, and then might get missed or overlaid by noise. What we choose usually is a theta smaller than t. T is now the relaxation oscillation time scale, so basically the inverse of the relaxation oscillation frequency. And then the nodes nicely depend on the neighboring states, emulates a network, and it was found to be a good range. But this would apply to a longer range. So, okay. So to conclude part 3, we have shown that there can be very competitive performance results for 2 computationally hard tasks, namely the spoken digit recognition, where we achieved a 0-word error rate as the best performance, and for the time series prediction, we had the best value of the normalized mean square error of 0.02, which is of the order of results obtained by other delay systems as well. Some are a bit better, but then also some of the pre-processing includes a bit of a memory, so the system performs better. Separation theta, and we have seen that if we read out the intensities from both modes separately, so polarization sensitive mode readout, this can, in the prof scheme at least, improve the results. The experimental dependence have qualitatively been reproduced such that close to threshold the results are best, and there's an increase for larger perm-currents. And all in all, this indicates that single delay systems using a semiconductor laser can be used for fast, efficient data processing, computation, or classification. But one can also think of later integrated devices. That comes to the end. So I have presented you with results concerning the synchronization of delay-coupled chaotic systems. I've shown how, for example, chaotic semiconductor laser dynamics can be synchronized, how it can be done, how asymmetries degrade this synchronization and or might change the dynamics, and how also intermittently occurring desynchronization decreases the correlation as well. Method was based on synchronization to basically assign determinism to radically occurring significant event, which can also be used for other systems. We just have to have significant event, and the system has to be synchronizable. And I've shown that within the concept of reservoir computing, one can use the transient dynamics of a single semiconductor laser delay node for very efficient data processing and computation. I would like to thank you all, especially you, and my advisor, Ingo Fischer, and all my collaborators that are listed here. And also I want to acknowledge, thank you.
Thank you, Konstantin, for your clear presentation. We are going to wait some minutes before question, or anyone wants to leave? No, la gente se va. Sorry for this way.
Very fine.
I think we can start with questions.
Thank you, Konstantin. I really appreciate the presentation, very clear, also from the aesthetic point of view, very nice presentation, nicely organized also. I also appreciate a lot the manuscript, which is really well structured, with a lot of interesting information, demonstrating actually a really broad work, and I would particularly emphasize as an experiment, even if you admitted that you did not do directly the experiments, but at least you were
I did some actually. I mean,
okay.
the ones that are in there I did, but the reservoir computing experiments that was done by Daniel Brunner and others, but not by me. I should admit that.
But anyway, I really appreciate this combination, which is according to me one of the best ones, to really combine all the different expertise, especially the ones you do have here right now, with this very nice experiment. Modeling of the lasers, the coupled lasers, different configuration. Could you give a little bit more details about the importance of the phase and the feedback phase, more specifically? How do you consider this phase in the models, and how critical is this feedback phase, the optical feedback phase, in the different equations and in the different results you present?
Right. Okay. First, in the model, in our approach or in my numerics, the feedback phase I set to 0. So I did not consider the influence of the feedback phase, neither the coupling phase. But also for a very long delay, and let's say not too strong feedback phase offset should not have a large effect on the synchronization.
Okay, that was the main motivation why